Hello guys, if you are watching this, that means you are on day 2 of material for this week. So you should have already watched the lecture and taken notes on plate tectonics and plate tectonic boundaries. So that should already be done before you go into this. So if you haven't done that yet, please stop this video and go back and do the other one. On a different note, please enjoy the shirt. It says blood type Little Debbie because the Little Debbie Christmas tree cakes are the best. And also, if we were in person, I would be recording this on pajama day. So, because I am the fun earth science teacher, be prepared for my slippers. I am wearing dinosaur slippers. I wish I were here to enjoy them with me. But all of the other teachers have gotten a fun chuckle out of them. And one of the janitors, or not janitors, but one of the workmen that come here and fix stuff, he started dying laughing. I thought he was going to have problems breathing for a second. But yeah, they're fun and comfortable. I wish you were here to see the slippers. But that was just a little side note. Anyways, again, sad y'all are not here this week. But in this video, we are going to talk about seafloor spreading. So I will go ahead and start this presentation. Again, if I'm looking down here and it's like, oh, what is she looking at? I'm looking at the notes. Just like all the other ones, I'm going to look at the notes. I'm going to talk about the PowerPoint, and that's how we're going to do that. So we are going to present this. Okay. So, tectonic plate boundary review. So this picture kind of encompasses all the different boundaries that we've already talked about. These little symbols here are talking about a convection sail. So right here, this is where two plates are pulling apart. So those types of plate boundaries is called a divergent plate boundary. Right here, where we see this kind of ridge forming, that is called a subduction zone. So that's whenever two plates come together. One is more dense, so it goes underneath. And that's what kind of forms this right here. That is a convergent plate boundary. We have another divergent boundary here on land. So again, those plates are being pulled this way. We have another convergent boundary over here on the edge of the picture. You are not going to get a subduction zone there, but you will get mountains forming because they're being pushed together. But they're the same density, so they're going to go up. And then on this other side, we have another converging, and the subduction zone is going this way, and that's creating a mountain change. So again, you have two main types, well, actually three main types. You have convergent, which is going together, which will go up or it'll go under. And then you have divergent, that's where they're pulling apart. And not pictured here is a strike slip or a transform fault, and that's where it's going to go past each other like this. So it would be something like that. So those are your three main types. Remember, there's two convergent. We have subduction and then just regular convergent. So seafloor spreading. It is a specific type of divergent plate boundary. So the first blank on your notes here, a process that forms. What do you think it forms? It forms new seafloor. So, for it to form new seafloor, some things have to happen. So we know that the plates have to be pulled apart. But those plates are being pushed apart, so like here are the plates. The plates are being pushed apart due to these convection cells. And the convection cells are made because magma rises up. So you can see that here, magma rises up. And as it rises, it cools, and then it goes back down. That's the convection type stuff. And then magma rises up on the floor, where it then splits apart and creates new floor. So magma rises up on the ocean floor where it splits. This makes new ocean floor. Seafloor spreading occurs at, so seafloor spreading occurs at mid-ocean ridges, and these boundaries are also known as divergent boundaries. So on your notes, there's a little picture there that looks very similar to this. It's just not as labeled. So if you are printing these out and drawing on them or writing on them, you need to draw in these little convection cells. And hopefully you remember what a convection cell is, because we've talked about it in every single unit that we've talked about. So it's where the hotter material rises, it cools down, and then it gets pulled back down because of the density changes. So let's see here. This is just another picture of that. Here are different plate boundaries that we saw something similar to in the last video. And again, it's just showing you different things that form because of these different boundaries. So where is the youngest oceanic crust located? So this is kind of trippy because we're used to seeing the land color, but here instead the seafloor is colored by age. So in the key up here, it shows that red is the youngest, from 0 to 2 million years old. And if we look here, there are certain lines of red. So on your notes here, it says, where is the youngest oceanic crust located? In the blank of the ridge. So in the middle of the ridge. These are your mid-ocean ridges. So this is North America, South America, Europe, Africa. So this is going to be your mid-Atlantic ridge. So in the middle of that ridge is where your youngest rock is, because that's whenever the magma comes up and it cools, and that's your new oceanic floor. So, underneath 2 on your notes, where it says the blank oceanic crust. So the youngest oceanic crust is in the middle at mid-Atlantic or mid-oceanic ridges. The oldest crust is near the continents. So, sorry, I forgot to revise these notes. I don't really like these notes. So the oldest oceanic crust is near the continents at the coast. Let's just put coast there. So you can see here, all around the continents is where your oldest oceanic floor is. And another important thing to see here is if you look at this ridge, you can kind of see a pattern. So on the direct sides of the ridge, you have the same color, and then the same color, and then the same color. So for your third blank right there underneath 2, or your third bullet, you're going to want to put the ages of the ocean floor mirror each other, because it's going to be almost the same thing here as it is here, because at this ridge, the plates are pulling apart. So as they pull apart, the new floor is formed right there, and then that gets pulled apart. But that was the same exact ocean floor or rock that was being formed, so they're going to mirror each other on each side of the ridge. So that mirroring effect kind of tells us a lot about the ocean floor whenever we look at it. So, here's the actual blanks. Sorry, I'm a little bit ahead of myself. So, the youngest oceanic crust is at the center at mid-ocean ridges. The older oceanic crust is near the continents at subduction zones, not the coast. Sorry, I told you wrong. And then the ages of the ocean floor mirror each other from the center. So those are your blanks for number 2. All right, so does the center of the ridge always show the current magnetic orientation of the north and south poles? Yes. The current magnetic orientation is indicated at the center. This is because certain rock types, especially the rock that forms the oceanic crust, records magnetic orientation. So the one in the center is going to be your most current magnetic orientation. But in the past, our compass needles pointed to magnetic south. So before they pointed to magnetic north, they pointed south. And this is a cycle. So we know that the North and South Pole is a little bit different than the magnetic North and South Pole. And this is shown in the rock history. So the magnetic iron in the lava points, or right there where the new rock is forming, the magnetic iron either points north or south, and it forms different bands of rocks on each side of the mid-ocean ridge. And these bands, they show what the magnetic orientation was during the time that rock was forming. So they show periods of magnetic reversals. So as you can see here in this picture, we've got the middle where the lava is coming up and forming new rock. So that's right here. It's recording whatever the orientation is. And then the rock before that, the rock band before that, would have been the opposite orientation. And so on and so on. As you can see, on each side of the ridge, again, you see the mirroring effect. So again, here's just another period here. Throughout all of this rock being formed, you have the same magnetism, and then it switches. So once that magnetism switches, you have a different rock, and then it switches again back to the other position. Again, you can see the mirroring on each side. When this rock is forming, it's all the same rock, and then as the plates pull apart, that rock gets split, and then it goes to the next one, and so on. So again, this is just another review of the different plate boundaries. We've got convergent when they come together, divergent when they pull apart, and then transform whenever they go past each other. Let's see. So in your notes, we want you to label what these things are. So first off, let's start with A. This is going to be a convection cell. Again, the type of heat transfer we've talked about all semester. So these are convection cells. And then B. This is going to be a divergent plate boundary, because it's divergent from one another. And then C, this is going to be a subduction zone. And then D, this is way back in our oceanography unit. What is this deep thing right here called? D is this deepest part of the ocean floor. This is going to be called a trench. It's also labeled right here. D is the trench. And then for E, what do we call this? This is where your new oceanic floor is forming. E is going to be your oceanic ridge. And then F. Again, whenever you go to label F, you need to ask yourself, is it above the surface or below the surface? And since it's below the surface, we're going to say F is magma. So convection cell, divergent plate boundary, subduction zone, a trench, an oceanic ridge, and then magma. So again, convection currents, you need to know that. Convection heat transfer causes these convection currents, which then cause magma to rise up at these divergent plate boundaries. So this one was a relatively short lecture. Has some oceanography review and the plate boundaries review. So after this, I will be talking about mountains. So those are some of the features that occur because of convergent plate boundaries. So I will see you in the next video. Bye, guys.